Since there is not one large common brain, there is also not one large common hologram. Each individual human brain receives and translates its own separate, individual, and uniquely downloaded hologram. If there was a common hologram, one big hologram of the universe for everyone, then we would each see reality exactly the same. And that doesn't happen. We all see reality just a little differently. For example, we're walking down the street, and you suddenly stop and excitedly tell me, hey, that guy looks exactly like Brad Pitt. And I turn to you and say, no, he doesn't. He doesn't look anything like Brad Pitt. What's happened here? You have seen pictures and movies of Brad Pitt, and you have an image of what you've seen. I could have seen those very same pictures and movies, but I have a different image of Brad Pitt. So when we see the same man on the street, he can look like your Brad Pitt to you, but he doesn't look like my Brad Pitt to me. If there were only one Brad Pitt that everyone saw in the same way, this kind of thing couldn't happen. But actually, we each see Brad Pitt a little differently. Or we're leaving a restaurant and you say, "Can you believe how rude that waitress was?" And I reply, I thought she was fine. She wasn't rude to me. Same thing applies. I perceive the waitress one way, and you perceive that same waitress in a different way, because we are experiencing the waitress in separate holograms. And we all know that 10 different people can have 10 different stories of how an accident happened. Now, these are small, minor examples, but our mental hospitals are full of people who see a very different reality than the rest of us, so different that they cannot handle it, and neither can society handle them. So each individual must have their own unique hologram they are projecting, their own private reality, especially since we each have an individual brain receiving our own personal holographic downloads. Besides, if there were one giant hologram we are all part of, it would mean there would be an independent, objective reality out there, and all the experts say that's not true.
There is no out there out there.
There's no out there out there.
There's an old New Age saying, you create your own reality. While this is technically not true, what is true is that you are projecting your own unique holographic 3D experience that has been downloaded from the field to your brain. It's time to pull together everything we have learned in parts 1 and 2 of this workshop series. We started with the double slit experiment, and we're going to end that way as well. Remember, physicist Richard Feynman has been quoted as saying that if you really understand the double slit experiment, you can understand all of quantum physics. So let's see what the double slit experiment says about the existence of an independent, objective reality out there. This time, listen to physicist Thomas Campbell from December of 2011. One quick note, Dr. Campbell is going to use the words diffraction pattern instead of interference pattern that we were using in part 1. Basically, they're the same thing.
This is a double slit experiment. It's a very famous experiment. This experiment has probably been done more times, more places, by more people than any other single experiment in the history of science. And it's because it gives such strange results that everybody wants to do it and see if it works like that for them. So this has been replicated over and over and over again, and whenever done properly, it always gives the same results. It tells us something very important about the nature of reality. Here's what happened, and I'll show you why it is such a famous experiment. Early on, we knew that waves, if you had a wave came to this thing, we have a barrier, a hole, a barrier, and a hole. That's called a slit. And it's two of them. There's a double slit. That's where the experiment comes from. That if a wave came here, some of the wave would go through this slit, some of the wave would go through that slit, and the distance from here to here is a little shorter than it is from here to here, right? We can see that. That's pretty obvious. If that difference in distance turns out to be like this, so the wave coming from the top hole and the bottom hole are shifted in distance one whole wavelength, then they both dip at the same time, they both crest at the same time, and you get a spot of light there. But if they happen to be just that difference in distance, where one gets to a peak just as the other one gets to a hump, you add them together, you get nothing. That's why you get nothing there. So what happens is you get this series of spots. It's called a diffraction pattern when you have waves going through the two slits. So they did this experiment with the double slit. They found a way to just fire one photon at a time at the slits, a particle. What they expected to see was this. What they saw was a diffraction pattern. Okay, now that was a surprise. They didn't expect that. So they said, well, there's something funny going on here at these slits. So these little red things are detectors. And they said, we're going to put detectors there at these slits, and we're going to see what's going on. And they did. They detected every time a photon went through this slit, this detectors would say, it went through the upper slit, or the detectors would say it went through the bottom slit. And whenever they did that, they got this pattern. So now the problem was, we take the detectors away, and you get this pattern. Then the idea was those detectors, they're doing something there. But they found out, and these are called quantum erasure experiments, they found out that you could take this data with these detectors, take all the data, detectors are working, it tells you exactly what slit each one goes through, but you don't look at this data, and you don't look at that data yet, you just take it. Now, if you look at it, you'll get this. But if you don't look at it, and then you erase this information of which slit they went through, you get this again. You see? So, obviously, reality is not objective. That's the double slit experiment, and that's why this is such a big deal, because it shows that reality is not objective. There's something else going on here. That's what we want to talk about. Well, I will give you a little experiment that I'm going to make up. This is not an actual experiment, what I'm going to tell you. This is just a logical equivalent, so it's easy for you to follow and understand. Actual physics experiments are very complicated, and they're very hard to explain, but this is, like I say, a logical equivalent. Let's say that we take 102 of this experiment. In other words, we're going to measure what slit it goes through, and then we're going to keep track of what happens over here on the screen. And we're going to do that just 102 times. And we're going to take data for an hour, put that in the computer, take the data again for another hour, put that in. And what we'll do is the first one we'll take this data, put it in an envelope, call it detector data, experiment 1, and we'll take this, put it in another envelope, call it measurement screen data, experiment 1, put those two envelopes into a big envelope and call it experiment 1. You with me with that? So I got an envelope that says experiment 1, and I've got, inside that, I've got two envelopes. One of them says detector data for experiment 1, the other one says measurement screen. So I've got all my data in here. So that's just an easy way for us to keep them straight. So we're going to do that 102 times, and because we're doing this experiment, we always expect that as the result. So after we have 102 of them, we look at the first one we did, and we take this data out of the envelope, take that data out of the envelope, and this is exactly what we see, just what we expected. That's the experiment we're doing. And then we take the last one we did, and we do the same thing. We want to make sure that they're the same, right, on both ends. So we do that, and we get exactly this. We get the two spots of light here is what we get. So the first one and the last one are like that. We assume all the ones in the middle were like that because they were all just done together. All right, but now what this delayed quantum erasure means is that let's take the 100 envelopes that are left, right? We got rid of number 1, we got rid of the first one and the last one. Now we have 100 left out of the 102. We'll take those 100 and we'll shuffle them, we'll randomize them up. Then we'll deal them out into two piles of 50. Now, one pile of 50, we will look at them, we'll take the envelopes out and look at them, and every one of them, all 50 of them, will look just like this. We have the two spots here. Now the other 50, we'll take out the detector data of each one of the 50, put them in a pile, and set fire to them. We're going to burn them. We're going to destroy them. That's our eraser experiment. Okay? I'm making a very simple concept in the eraser experiment. We just burn them and destroy them. And no, they're not still readable in the ashes. We'll take the ashes and put them in water or something. Don't complicate the experiment. We're just going to burn them. That's going to get rid of them, and they will be erased. And then we'll open up these envelopes, and every one of them will be a diffraction pattern. You see? That's what I mean by a delayed quantum erasure experiment. Every one of them will be. And you're thinking, how could that happen? You see, the experiment was done, let's say, a year ago before we took these envelopes out and sorted them. It doesn't matter. 10 years ago. The amount of time is irrelevant. In these experiments, they're actually done like 10 nanoseconds. But it doesn't matter. If you can do it in arrears, you can do it any amount of time. So that's why this is weird science. It looks like, depending on what you do with this data, you make this change from this output to that output, right? That's what it looks like. But that's just because you believe you live in an objective reality. You see, in a statistical probability reality, this is still indeterminate. It hasn't happened yet because you haven't looked. You see, you don't know what it is. In an objective reality, you know because you did this experiment, that's what it had to be. So you believe that's the way it is, and then you somehow magically changed it to this. Well, there's no magic involved. It's just that because this data hasn't been looked at, it doesn't really exist yet in this reality. Because we live in a probabilistic reality. I know you're thinking, that sounds impossible, but that's because you are ingrained from your culture with the concept of an objective reality. You believe that's the way it is, so when you see this or hear about it, it just doesn't make sense. Just like the world being around didn't make sense.
Let's make sure we all understand what Thomas Campbell just said. He said that we have to actually look at, to observe, the measurement data taken at the two slits in order to get a particle pattern as a result. If we don't look at the measurement data, if we erase that data without observing it, then we get what he called a diffraction pattern, which Captain Quantum called an interference pattern in Part 1. In other words, apparently it's not the act of measurement at the double slit that matters. The only thing that really matters is whether we look at the data we collected. If we look at the data, we get a particle pattern as the result. If we don't look at the data, we get an interference pattern that waves make, even though the data was collected. If there were some independent objective reality out there we all share, the result of the double-slit experiment would be the same all the time, regardless of whether someone looked at the data or not. What we have instead is a totally dependent, subjective holographic reality that is unique for each individual and based on their observation. In other words, what you are seeing right now, and every moment you are alive, without exception, is a holographic 3D total immersion movie written uniquely for you, downloaded to your brain, translated into the holograms you see, and projected out there for you to experience. That's worth repeating. What you are seeing right now, and every moment you are alive, without exception, is a holographic 3D total immersion movie written uniquely for you, downloaded to your brain, translated into the holograms you see, and projected out there for you to experience. Listen to Dr. Amit Goswami very carefully but actually we each see Brad Pitt a little differently. Or we're leaving a restaurant and you say, can you believe how rude that waitress was?" And I reply, I thought she was fine. She wasn't rude to me." Same thing applies. I perceive the waitress one way, and you perceive that same waitress in a different way. Because we are since there is not one large common brain, there is also not one large common hologram. Each individual human brain receives and translates its own separate, individual, and uniquely downloaded hologram. If there was a common hologram, one big hologram of the universe for everyone, then we would each see reality exactly the same. You have an image of what you've seen. I could have seen those very same pictures and movies, but I have a different image of Brad Pitt. So when we see the same man on the street, he can look like your Brad Pitt to you, but he doesn't look like my Brad Pitt to me. If there were only one Brad Pitt that everyone saw in the same way, this kind of thing couldn't happen. And that doesn't happen. We all see reality just a little differently. For example, we're walking down the street, and you suddenly stop and excitedly tell me, hey, that guy looks exactly like Brad Pitt." And I turn to you and say, "No, he doesn't. He doesn't look anything like Brad Pitt." What's happened here? You have seen pictures and movies of Brad Pitt, and you're experiencing the waitress in separate holograms. And we all know that 10 different people can have 10 different stories of how an accident happened. Now, these are small, minor examples. But our mental hospitals are full of people who see a very different reality than the rest of us. So different that they cannot handle it, and neither can society handle them.